For centuries, humanity has gazed at the night sky, wondering about the nature of the cosmos and our place within it. With the advent of modern cosmology and theoretical physics, questions about the origin and ultimate fate of the universe have taken center stage. While numerous theories attempt to describe how the universe might end, such as the Big Crunch, heat death, or vacuum decay, one of the most fascinating and terrifying among them is the Big Rip. This hypothesis proposes that the universe could be torn apart by its own expansion, driven by an unknown force commonly referred to as dark energy. In this essay, we will explore the science behind the Big Rip, how it compares to other end-of-the-universe theories, the role of dark energy, observational evidence, and the implications for the future of space, time, and matter. The idea that the universe is expanding was first proposed in the 1920s, when Edwin Hubble observed that distant galaxies are moving away from us. This observation formed the basis of what we now call the Hubble-Lemaitre law. The farther a galaxy is, the faster it appears to be moving away. This led to the realization that the universe is not static, but rather expanding in all directions. In the framework of Einstein's general theory of relativity, this expansion is described by solutions to the Friedmann equations, which relate the curvature of space, the rate of expansion, described by the Hubble parameter, and the content of the universe, including matter, radiation, and dark energy. In 1998, two independent research teams, the Supernova Cosmology Project and the High Z Supernova Search Team, made a groundbreaking discovery. By observing type Ischia supernovae, they concluded that the universe's expansion is not just continuing, but accelerating. This unexpected result required an explanation, which came in the form of a mysterious force or energy now called dark energy, which makes up approximately 68% of the universe. Unlike matter and radiation, dark energy exerts negative pressure, driving the acceleration of cosmic expansion. Despite its name, dark energy remains one of the least understood components of the cosmos. It is invisible, does not interact with light or ordinary matter except gravitationally, and its properties are still largely theoretical. There are several leading hypotheses. Cosmological constant, lambda. Originally introduced by Einstein, this model treats dark energy as a constant energy density filling space homogeneously. Quintessence, a dynamic field that changes over time with properties similar to a scalar field. Phantom energy, a form of dark energy with an equation of state parameter, dUW, less than -1. This type is central to the Big Rip scenario. The equation of state parameter dW is defined as the ratio of pressure to energy density. For dark energy, if W equals -1, cosmological constant. If W is greater than -1, quintessence. If W is less than -1, phantom energy. The Big Rip theory was proposed in 2003 by physicists Robert R. Caldwell, Mark Kamienkowski, and Neil Weinberg. It is based on the idea that if the universe contains phantom energy, W less than -1, the expansion rate will not only continue to accelerate, but will do so at an increasingly dramatic pace. Unlike a constant expansion rate or one that slows over time, the Big Rip suggests a runaway expansion, where the repulsive force of phantom energy grows without bounds. Eventually, it will become strong enough to overcome every fundamental force in the universe, leading to a cosmic catastrophe where all matter is torn apart. The sequence of events in a Big Rip universe unfolds as follows. Billions of years before the Big Rip, the increasing expansion begins to tear apart gravitationally bound systems. Galaxy clusters currently held together by gravity will be the first to disband. Closer to the final moment, individual galaxies like the Milky Way will unravel as the expansion overcomes the gravitational pull, binding stars in orbit. As the rip grows stronger, solar systems disintegrate. Planets are flung away from stars as their orbits are disrupted. Eventually, Earth and other planets will be torn from within, their atoms scattered as molecular bonds fail under the immense force. In the final moments, possibly just seconds before the end, the expansion becomes so extreme that even the atomic nucleus is unable to withstand the force. Protons, neutrons, and electrons will be separated and scattered into oblivion. Caldwell and colleagues estimated that the Big Rip could occur in approximately 22 billion years, depending on the exact value of W. Here's a sample timeline based on this estimation. 60 million years before the Rip, Milky Way is torn apart. 3 months before the Rip, the solar system unbinds. 30 minutes before the Rip, Earth is destroyed. 10 to the power of negative 19 seconds before the Rip, atoms disintegrate. This rapid escalation is due to the exponential growth of expansion, making the Big Rip not just a distant possibility, but a sudden and violent finale. This is the most widely accepted scenario. The universe continues expanding forever, but at a decelerating or steady pace. Over trillions of years, stars burn out, black holes evaporate, and the universe approaches thermodynamic equilibrium, cold, dark, and lifeless. This theory posits that the expansion will reverse, causing the universe to contract back into a singularity. However, this requires a high density of matter, which current measurements do not support. If our universe resides in a false vacuum, it could suddenly tunnel into a lower energy state. This transition would cause a bubble of destruction to expand at the speed of light, annihilating everything it touches. The Big Rip is unique among these in that it preserves the expansion but weaponizes it, turning the very fabric of space into the agent of destruction. So, is the Big Rip the most likely fate of the universe? Observational data from Planck, WMOP, and supernova surveys indicate that the equation of state parameter W is very close to -1, but we are not yet certain whether it's slightly above or below that threshold. The most recent data suggest W approximately equals -1 plus or minus 0.05. This range keeps all major scenarios on the table. However, if future data conclusively shows W less than -1, then phantom energy becomes the leading candidate, and the Big Rip becomes not just plausible but probable. Advanced projects like the Euclid Telescope, ESA, and the Nancy Grace Roman Space Telescope, NASA, aim to study dark energy with unprecedented precision. The Big Rip poses profound questions. Causality. If atoms are destroyed, do the laws of physics remain valid? Time and space. If space itself is destroyed, does time cease to exist? Fate of consciousness. If everything is torn apart, including the neurons in our brains, is there any room for survival, even theoretical? It also challenges our understanding of energy conservation. Phantom energy leads to increasing energy density, which seems to violate known physical laws unless deeper frameworks, perhaps from quantum gravity, come into play. Some theories suggest that the Big Rip might be avoided or modified by quantum effects. Quantum gravity. In theories like loop quantum gravity, space-time is quantized and may resist infinite expansion. String theory. Some models within string theory include mechanisms that prevent W from dropping below -1. Brain cosmology. If our universe is a brain in higher dimensional space, the Big Rip may be an artifact of our limited perspective. In other words, the ultimate fate of the universe may lie not in classical physics, but in a unified theory that blends quantum mechanics with general relativity. While the destruction is complete and absolute, theoretical speculation has no bounds. Some ideas include escape to another universe. If multiverse theories are valid, advanced civilizations might find a way to tunnel to another universe. Uploading consciousness. Though atoms are destroyed, perhaps data encoded in exotic media could survive in quantum fluctuations. Technological shielding. A civilization millions of years ahead could attempt to create an artificial pocket of space-time immune to expansion. While these ideas are deeply speculative, They underscore humanity's instinct to adapt and survive, even in the face of cosmic doom. The Big Rip represents one of the most dramatic and awe-inspiring possibilities for the end of our universe. Though it remains speculative and dependent on future data about dark energy, it is grounded in legitimate physics and mathematical models. Whether or not it becomes our fate, studying such scenarios forces us to confront the boundaries of knowledge, the nature of existence, and the fragility of everything we know. As we advance our understanding through observation and theory, the Big Rip remains a chilling reminder. The cosmos may one day not end in a bang or a whimper, but in a tear, ripping apart stars, atoms, and even the laws of physics themselves. If you found the mystery of the Big Rip fascinating and want to explore more mind-bending ideas about the universe, space-time, black holes, and the future of humanity, don't forget to subscribe. Stay tuned for more in-depth explorations into science, cosmology, and the universe's greatest enigmas. Hit that subscribe button and join our mission to understand the cosmos, one theory at a time.